In the government's latest response,
you must stay at home.
Master of the house, doling out the charm.
It's very important that everyone
know that you are not alone.
All right, today, no, not doing the accent. Okay, so today we're going to talk about Maxwell's equations and how this sort of comes to electromagnetic theory and how it's this beautiful coming together of various equations that Maxwell's gathered and understood and put together. It's so much fun. Okay, so let's talk about electromagnetic theory and what sort of is the culmination of classical electromagnetism. So, our learning goal here is to be able to understand and explain qualitatively. So you need to be able to reproduce the equations and talk about them, but not do the equations. Okay, like this is so far beyond the high school mathematics of what we're talking about. So we want to be able to refer to the equations and talk about James Clerk Maxwell's unification of magnetism and electricity, which is kind of this really cool thing. All right, so here's your vocabulary. If I could just get you to pause the video here, hit subscribe, hit like, all that sort of stuff, and write down these. You write down these words, so you've got to refer back to as we move through the unit or through the lesson. So, once upon a time, when the world was dark, there were two separate ideas. There was electricity, and then there was magnetism. And then comes a group of ideas which are put together by, so the work of various scientists is put together by James Clerk Maxwell. That's why he's in the red outfit. And when they unify together, all of a sudden, we have a solid understanding of electromagnetism. They are no longer these separate powers or forces in the universe. They are but one force together. So Maxwell's equations and the way they describe, there's four of them, right? Four we're going to refer to. And again, we're looking at this from a descriptive standpoint. So we've got the Gauss's electric flux equation. So it's this, right? So the electric flux of over a surface, let's write a little circle around there, times the square, or times the area, sorry. This is an integral function, or an integral. And we see we've got vectors here, equals the total charge divided by the permittivity of, I gotta get confused with the permeability, the permittivity of free space, which is the electric constant, right? Like how much the electric field can move through a vacuum. So, here we have here. So we've got the integral, this whole thing's an integral. There's another form of this. We're going to stick with the integral form because it makes a bit more sense in a high school setting. So we've got the electric field, the surface area, and that's this surface area. So this is a charge, right? And a charge, all of the, so what this is telling us, so all of the all of the field permeates out radially, and it moves out through an imaginary surface. So if we put the surface here, if we did this with a circle, a sphere, that's actually pretty easy to work out. But if, like we see these sort of Gaussian fields here, even if it's not a sphere, by using the integral, we're able to break it down into essentially infinitely small pieces and add it all together and work out what the total surface area is going to be, and what the electric field is passing through that. So, the enclosed charge divided by the permittivity of free space, what this means is that the electric flux moving through a closed surface, an imaginary surface, through a closed surface, is proportional to the total charge inside, so enclosed by that surface. And that means it's a non-zero number, so that's important. All right, so then we move on to Gauss's magnetic flux equation. So what we see here, this is our field. We've got a north and a south pole. Remember, dipoles are the only way magnets exist, but under standard conditions, monopoles don't exist. So what we see here is we have a closed surface, And the flux lines, or the fields, the force of the fields, move through, and they cancel each other out. So every field that leaves, it enters back in, and we end up with a net zero. So B being a magnetic field, again, the area equals zero. And that's important too, right? That's going to come involved. So then we get to Faraday. Now Faraday, bit of a big dog in physics, particularly this field. He and Oersted were the guys who really sort of put together that electricity and magnetism, there's something going on there. So the electromotive force, so just a voltage. So let's have a look. So this is the Maxwell version of the Faraday equations, or Faraday work. So integral here, the integral of the electric field, the infinitesimal. So basically a point element of a closed loop equals the negative change in the magnetic field flux divided by the change in time. So what this means is that a change in magnetic field causes an electric field. Okay. So there's an EMF, a electromotive force. So I get really excited about it. So the words are slipping around. Electromotive force induced by a change in magnetic field. What? Now, one of the things that James Clerk Maxwell he understood symmetry, and if there's likely to be a change in, so we see how the two Gauss equations are related. If there's likely to be a change in, so a change in magnetic field creates an electric field, he understands that it's likely to go the other way as well. And that's where the Ampere Maxwell equation comes in. So here we have the magnetic field and the infinitesimal element, I really like that word, of a closed loop is equal to the permeability of free space multiplied by the current divided by the displacement current. Now, displacement current is not a real current, it's to do with the movement of the electromagnetic field, and the displacement current is equal to the permeability of free space multiplied by the flux, change in flux. Sorry, there we go. You're confused. So it's change in electrical flux divided by the change in the time. We're getting there. Okay, so it's all there, right? So what this means is that the flux, the field strength of the magnetic field multiplied by with a infinitesimal element of closed loop is equal to the permeability of free space, that's how far the magnetic field is able to move in a vacuum, multiplied by the current, plus permeability of free space, multiplied by the permittivity of free space, multiplied by the flux of the electric field, change in flux divided by the change in time. Okay, so what does all that mean? That means that a change in flux results in a change in, so when that's zero, right? There's nothing going on. But when there is a change in flux and a change in time, there will be a change in, there will be a magnetic field. Okay? So, well, a change in electric field induces a magnetic field. So this and the Faraday equation come together, right? So when one changes, it causes the other to be induced, which is a change, which then causes the other to be induced, which is a change, which then causes the other to be induced, which is a change, and therefore the electromagnetic wave is able to propagate, so move without a medium. What? I know, it's fun. So we combine the four equations. We've got the propagation of electromagnetic waves. See what I mean? Like they move in the same direction. Electricity, magnetism, moving in this direction, or the energy is moving in this direction, the particle, but the wave, and they are in phase with each other. So that's cool too. Okay, so we have a change in electric field. So for example, if we oscillated a charged particle, we would have a change in electric field because the electric field would move, which induces a magnetic field, which then causes a change in the magnetic field, which will induce an electric field. So if we have a particle here oscillating up and down, the light wave will move out. And that's kind of awesome. So these equations together show that an electromagnetic wave together, like that, is self-propagating, and it can move through a vacuum. No medium is required. So, but he wasn't stopped there. He wasn't stopped there. So he's got a couple more derivations that are important to us. First off is we have the ability to describe it as a wave. And we see this here, right? So this is describing a wave as it moves up, okay? So as this one moves up, it moves across. So we've got a wave. That's pretty rad, right? So these derivations show that we have perpendicular waves moving like this, yeah? In phase, periodic, and propagating. But he also gets to this point. So the speed of an electromagnetic wave is the electric field magnitude divided by the magnetic field magnitude. So these are just some more derivations of what he's got earlier. Therefore, they equal 1 over the square root of the permeativity of free space multiplied by the permeability of free space. Again, we don't need to know how we got there. We just need to know that this is where he is. And because these two numbers are constant, that means the speed is constant for a wave, and the velocity for an electromagnetic wave in a vacuum is 2.998 times 10 to the power of 8 meters per second. It does not change. It's a little bit of a coincidence that it's also the speed of light. So I find that really amazing. He was able to work all this out using maths. And then what's more from there is that, as we said, and what that shows us is that these constant values, speed of light is constant, speed of the electromagnetic wave is constant, and it is the same as the speed of light. Therefore, light is an electromagnetic wave, can be propagated on its own from an oscillating charge. And that's how it was worked out with maths. It's kind of beautiful, and I really love it. And I hope you did too. I hope you got lots of cool notes. I hope you've got lots of questions. Any questions you have, put them in the comments below, and we'll get back to you as soon as we can. Thank you for watching, and subscribe and like and all that sort of stuff. And we'll see you next time. Bye now.